Okay, so the last talk of this morning is by Iskander, who is going to talk about punctual structures relative to oracles.
Okay, thanks. Thanks to organizers for inviting me. So I will start. So I will speak about some questions in computable structure theory, and my approach is a little bit different from a classical one, classical approaches. In particular, when I study some algebraic structure on the domain n, on the set of natural numbers, I will identify the functions on n. I will identify it with the one function fa, which is a join of all operations and predicates in the language of the structure. So the structure I consider only finite languages, so it can contain some finitely many operations, functional symbols with different arity and different predicates, also with different arity. And I just, because the universe is fixed, I just identify the structure with from the computation, from a computability point of view, with the join of all functions and operations. And so it's what it means. We just forget about the arity. We just glue the tuples into the numbers by the standard coding of tuples. And so it's just, we can consider it as the functions with two arguments. One is just index, finite in a finite interval, and another is just a tuple corresponding to the is function or operation. So it is it's quite obvious that we can make such identifications, but more standard way when in computable structure theory is just to consider the atomic diagram of A. So it is a set of atomic formula which are true in the structure A. But the atomic diagram is a set, not a function. And of course, there are another way just to reduce the functional symbols to predicates. Is just to, we can in computable structure theory, it's very often we just transform the operations into the predicates, just replacing the functions by their graphs. So it's also typical question, typical considerations, but I will study the function. The reason is why, because I'm studying about some not general computability, but more, in some sub-recursive meaning, using primitive recursiveness. But still, the function fa as defined also can be used in the classical settings. So an algebraic structure is computable if and only if it's this function is computable. But if we consider primitive recursiveness instead of computability, then it is essential that we still consider function, not operation. So the term of punctual or fully primitive recursive was introduced in our joint paper with Sasha Melnikov and Kengmeng Eng. Of course, it is there are another papers and studies of the primitive recursive structures. But we decided to concentrate on that case. Then the universe is good. It is not a subset of primitive. It's not a primitive recursive subset of N. We consider exactly the structures on the good universe N, and it will. We found that it's quite natural exactly to consider that case. Some of the results connected with this approach I will show. So the structure is punctual if exactly this function is which I defined just before is a primitive recursive, and of course we cannot replace the functions by some 0, 1 valued function. We cannot replace the operations here by a predicate. We cannot do that reduction. It's a different operations have a sense. Okay, but today I will speak about the analogous of the notion of the degree spectrum. And first, I will speak about two different definitions of degree spectrum which exists in classical computable structure theory. First one is just a collection of Turing degrees of different isomorphic copies of the structure B on the domain N. So the structure can be considered can be presented on the set of measures by different ways, and we study all Turing degrees of that copies. So here we can still think that A is just the function fa. It's no matter here, but it's also can be considered as the function fa. So we identify fa and a in this talk. So the first definition is of the degree spectrum is exactly the collection of Turing degrees of the different presentations of fixed structure B. Another typical approach is we can define the degree spectrum is it's just upper closure of the first definition. The degree spectrum is all Turing oracles which compute an isomorphic copy of B of the domain. So it's all oracles which can compute something isomorphic to B. But usually it is no these definitions very closely related, and in most cases these two definitions produce one class because of result of Julie Knight from 1968. So it states that in most interesting cases, these definitions are the same. So there is only one trivial case when the degree spectrum in the first definition of degree spectrum is not closed upward. It's only when it's up to some finite set of constants, and all permutations are isomorphisms. So, for example, it's the most simple example of the structure is just empty structure. If a structure is empty, or for example, a graph with infinitely many edges, vertices, but no edges at all. It's just empty graph. Of course, any possible presentation of that empty graph must be computable. And so in this case, all copies are computable. And in fact, it's not so interesting from the point of view of Turing degrees. It's just zero, nothing. No, the similar situation can be if we add some new vertex into the empty graph, which is just connected with all other vertices. So it's again, it's any possible presentations must be computable. So it's up to some finite set. All permutations are automorphisms. If they are fixed some finite set of constant set, then it's automorphism. So it's a trivial case, not so interesting from the degree structure point of view. But in all other cases, we can code any information, any set, into some copy of A. You can make a copy a little bit harder than B itself. You just code the set X and into some isomorphic copy, and the degree of A will be exactly the degree of X, the Turing degree of X. And so it is. This theorem shows that in most interesting cases, we can use both definition as one object and study that object. It's either zero if I consider only finite. If the language is infinite, then we can get, of course, some copies will be not computable, maybe harder. But if the language is finite, then all copies must be computable in the second case of this theorem. In all other cases, it just close it upward, and so it's irrelevant which definition of degree spectrum we use. So now I am going to introduce the degree spectrum corresponding to the primitive recursive computation. So instead of the Turing reducibility, well-known Turing reducibility, I will use the primitive recursive reducibility, which is also quite natural. If you take the definition of primitive recursive functions, which is defined inductively by the operation of superposition and primitive recursion, then we just and there are some basic primitive recursive functions which generate all possible primitive recursive functions. Here we just can add some functions g as a new basic primitive recursive function, and we can start producing new functions. And if some function f produce it using this primitive recursive scheme, then we say that f is primitively recursively recursively reducible to G, if PR reducible to G. And it's obvious that this definition is transitive, reflexive, and so on. So it is very similar to all reducibilities. And in fact, it is in some point where it's very it's somehow similar to the truth table reducibilities. But of course, there are some differences. Most of them connected with in the bottom we have only primitive recursive functions and sets, not computable. And also here for this definition we must distinguish functions and sets. For Turing reducibility, it's relevant. Functions and sets we can replace the functions by the graphs and so on. But here, of course, it's not. But if f is primitive recursively bounded, so if fx is bound, the value is always bounded by some primitive recursive function. F may not primitive recursive itself, but if it is bounded, then it's easy to see that f is PR equivalent. So you can make reducibility on both sides. From f to graph, it's It's always we can do that, and vice versa. We can produce f using the graph. But it's only one case. In general, not. And how about the degree spectrum? So we have a primitive recursive reducibility. We have we know how to code how to consider a structure as a function. It's okay. And which definition now we need should choose, in fact, to make a similar definition for PR. And I found, so this is a new result appeared just while I'm preparing the talk, in fact. So it is not checked, but I am 99% sure that this is true. That if we consider the first, if we try to adopt the first definition of degree spectrum, so it is exactly the PR degrees or the presentations. Then we have we have no analog of the Knight theorem. So the structure can be non-trivial, but the collection of presentation is not closed under the PR reducibility. So and we get this only on the very simple language. It's just a functional unary structure, and it's in fact it's a permutation, but it's relevant. It's just a unary function, and it is not and it is infinite permutation. So it is it's not identity on infinitely many elements, and this provides that the structure is not trivial. If P equals to ID, so if P would be identity on all elements, then it's, of course, this is a trivial structure. Any permutation of that unary structure is an automorphism. But if P is not identity on infinitely many elements, of course, it's non-trivial. But still, this function, this permutation P is primitive recursive. So this structure is punctual. But we cannot make a copy which have the exact degree of C for some computable set C. So it is something strange fact, and in fact, I even do not know how we can improve or study that questions. Maybe it is a hard questions. So we have a problem here. Even a structure is a punctual, so it is must be sufficiently easy to study. But still, we do not know the possible collections. Some sets we can code, some sets we cannot code. I do not know. But it is some strange fact, which I just use it just as some strange fact, which I am going to avoid, because my results will study the second variant of the degree spectrum, which is closed upward from the beginning, exactly as in the Turing degree. So I'm from the beginning close the degree spectrum from oracles. So it is exactly the collection of primitive recursive oracles, which can primitive recursively compute some isomorphic copy of the structure B on the domain N. So it is all F such that there exists some A on the domain N, such that A as a function is primitively recursively derivable from F. But maybe there is some particular interest of studying that effect, but I am doing almost nothing about It's just a recent result which shows that it's not so easy, in fact. Maybe not easy. But I will study this. I fix this definition and study only this definition. Okay. Okay. And based on this definition, we can see a very also an unexpected fact. While in the functions and the sets in the PR is different. In fact, the primitive recursive degree spectrum, is punctual degree spectrum, is in fact is based on the sets, not on functions. So this proposition proved as a part of another proof. It's not stated in our joint work published in 2021. It's by me, Sasha Melnikov, and Antonio Montalban. So in fact, we can go from every possible structure to the recursively bounded structure. And based on, and because if a function is primitively recursively bounded, then the function is PR equivalent to the graph. So, so this punctual degree spectrum is based on the sets, not on a function. Below any function, below any element of the degree, we can fix some set. So it is a 0, 1 valued function, which also belongs to the degree spectrum. I will call this property set basis property, just for a future reference. So it is quite strange fact, but still it's it shows that what here functions and so the degrees of sets are enough to describe the possible degree spectrum, punctual degree spectrum. Okay, now we are going to inspect some basic knowledge about the Turing degree spectrum. So it is quite old observations, which goes from result of Richter, as I remember. So we can code any set into the Turing degrees. Now I'm saying the Turing, just I recall old results. So the Turing degree spectrum can be an upper cone in the Turing degrees. We can code any set in the bottom. So it's exactly all degrees which compute some fixed set. I will not speak how it's sufficiently easy and obvious how many possibilities. But it is interesting here that you can even find a model theoretic, computable model theoretic description of all the structures which code a fixed information, just some real C. A set C is computable in every copy. So it's exactly the case when we have the degree spectrum like that. Because in every copy of the structure A, if and only if this set is coded into the existential theory of that structure. So more formally, we can provide a computable mappings from natural numbers into the quantifier free formulas, phi n and psi n, such that n belongs to C if and only if in A there are some tuples satisfying the property phi n, and does not belong to C if and only if psi n is satisfiable by some tuple in A. up to some up to some tuple of parameters in A, which can be fixed from the beginning. So, and of course, if we, it is natural. So all such cases when some set C is coded into the all copies, they are can be provided by very natural way. It is, if this property holds, of course we can compute C in any copy. Just seeing this copy, studying the copy, and waiting while either this formula will be satisfied or this formula will be satisfied for specific n. So it is it's results in the Ashnight book. Maybe it's published somewhere else, but it's a forcing result. And it is interesting that we have some analog in the punctual case. Of course, again, we have some possibility to code a set into a structure. So we can have upper counts of PR degrees. Maybe not all possibilities to code a set which we used here can be adapted for PR, but some of them surely can be adapted. The most simple way is just take the structure on the n, on the set of natural n, we add the successor function, which is just x plus 1, and the set C, the original set C, we consider as a predicate, as unary predicate. And of course, in any copy of the structure, we can fix the 0, the element zamorphed to the 0, and just can repeatedly apply S function if it the primitive recursive scheme allows us to do these iterations. And after that, we just check the predicate C and that element and the derivative. So it is most simple example where we have this property. Of course, in every copy we can compute primitively recursively the set C, and vice versa. If F can be compute C primitively recursively, then we can make that that structure itself so good. But so we its structure is finely it's essential here that a function is finely generated. We can just start just to derive all elements from the 0. But it's interesting that we can find even not finely generated structure. So, for example, we can replace S by the following functions. It is a binary iteration, and the result is minimum from the x plus 1 and y. And now every finite tuple of elements generate only finitely many elements. You cannot cross the maximum, the original maximum of elements. But again, we have this property because we can use any elements. If you take sufficiently many elements, just randomly, just any, we can derive all. We can derive the element corresponding to 0, 1, 2, 3, and so on and so on. We just take any element, but the structure is locally finite itself. This is formally more difficult case, and in fact it's typical case in some sense, because there is an analog of S-Knight theorem, which shows when some set is primitive recursive in every copy of the structure. Again, oh, sorry, there are sorry, I need to fix here because it's primitive recursive, of course. Matrix, not computable. Otherwise, it's so again, almost the same. There are primitive recursive mappings into the quantitative free formulas, such that if n belongs to C, then the formula phi n satisfied in A for every possible tuple X in A of pairwisely distinct elements. So here we do not use existential quantifier. We do not use universal quantifier. It can be considered as very weak quantifier, which is say just irrelevant which tuple. It's the main thing. It's the tuple must contain different pairwisely distinct elements. And because the structure is based on the universum n, we can just take arbitrarily many elements. We can take any number of different pairwisely distinct elements and just use it for testing, for calculation, and belongs to C or not. So it is the result again by me, Sasha Melnikov, and Antonio Montalban, published in 2000 last year. So it is analog, full analog of the S-Knight theorem. But so it's interesting. We again have some property, model theoretic property describing this effect. And this example is exactly when we need to use this weak quantifier, which says that any pairwisely many element, any. This locally fine instruction. Here we do not use. We just can take 0 and produce everything. Here it is more difficult and so on, and more general in the sense of this type. Okay, so it is a cone. So the cones are possible, and they are described somehow. And another corollary from this result is about the it's unexpected, in fact, corollary. It's about the relational structures. If you see these examples, we see that we cannot omit. You cannot replace the operations here by relations, and in fact, it is true. So it's it follows from this theorem, from the specificity, from the properties of this weak quantifier, which we use here. So a reformulation of Ramsey's theorem states that every infinite relational structure contains an infinite homogeneous substructure. And using this reformulation, we see that we can reduce this question about the structure A, about its infinite substructure. And this infinite substructure can be very, very easy, in fact. And we even do not use the structure A itself. So in this case, C must be primitive recursive. So if degree spectrum is a cone and the structure is relational, it's no operation, then C is primitive recursive. So it is, in some sense, it is strange, in fact. So we know that the degree spectrum, punctual degree spectrum, is based on the 0, 1 valued function from one point of view. So we so we cannot code a function here instead of set. It's impossible. Only sets can be coded. But for that, even for that, we need operations in the structure. Relational structures just code nothing. And in general, I should say that a description of a degree spectrum of relational structure can be hard. I do not know. I didn't study it, but it seems it is hard. An example of it's quite difficult to get an example of relational structure without punctual presentations. So it is result of me, Melnikov, and Enge. We produced a graph which has no punctual presentations. But even for that example, it is difficult to say what is a degree spectrum. Okay. How about the cones? The cones, the unions about the cones. It's a photo results that the union of two upper cones is not a degree spectrum for the structure. It follows from the forcing like presented in this theorem. It's a forcing result which not so difficult. And it's Folker theorem. It's a well-known result. But now we can use the forcing in that theorem to get the similar result for PR degree. So the union of the two upper cones is not a punctual degree spectrum of structure. And now I will speak about the complement of lower cones. It's also there are results in that directions. First, of course, this is a well-known result of Schleiman and Wagner about the degree spectrum of all non-recursive oracles. This is a structure which is computable in all non-recursive structures. This theorem was adopted for another complements of lower cones. It's my results 2008. So it's a complement of 0 prime. It's also a degree spectrum, but for other jumps of 0, for 0 double, 0 triple, and so on, this is not true. This is a result of Andrews, Kay, me, Stefan Lemp, Antonio Montalban, and Joe Miller, 2016. So, so this is results about the lower complements of lower in Turing case. What's the situation? I should say that for the first result, Werner used a specific family, some diagonal family. I guess I don't have no time to just say about that. I should go to the questions about the primitive recursive punctual degree spectrum. So 2 questions. So is it possible that all non-primitive recursive oracles produce a primitive recursive spectrum? And for which other complements of lower cones are realizable as the punctual degree spectrum? And of course, we need first can check the set basis theorem, set basis property. If you test this collection, then you can get that that in fact this property passes. So if a function's g is not primitive recursive, then below that we can find a set x which is not primitive recursive. So, and it's interesting that the result is it looks like non-uniform, but it's uniform. And there is an example. Some set. I will not have no time to say it formally, but it's also an interesting example. So you can find some set, in fact, there are many such sets, computable sets, even computable sets, for which the test fails. So this collection have no set basis property. Some function belongs to that collection, and every set below that does not belong to this collection. And so for some sets, the complement of lower cone is not a punctual degree spectrum of structure. And so for 0, we have some chance to get a structure with the desired punctual degree spectrum. It's quite easy to code a countable family into the structure. It's quite a natural way. It's exactly as we code a specific set into the structure. We can code a family of sets into some specific structure, and this structure just gives the possibility to shuffle all these sets together. It's a quite standard way. I only use so it's a predicate, suggester function, some specific possibility to go up, and I need some root functions to just to have a possibility to read every set from the beginning. And we can code. This coding says the property. So if primitively recursive compute this structure if and only if there is some set y which primitively recursively enumerate the family. So f is exactly the collection of all columns of this set y. To make this proposition true, I exactly use this fictive parameter y, which gives a possibility to repeat every set of the family in the structure. And now, using this coding, we can present this specific diagonal family. It's in some sense, it is very similar to the Werner family, which is computably enumerable exactly in all non-zero oracles. Here it's exactly the same, but here there are some trick in this diagonalization. So we use Gödel numbering of all partial computable functions, and we use the Gödel numbering of all primitive recursive sets. And so the family consists all the sets of the form n plus f. F is finite subset of natural numbers. And if it's with only one restriction, if phi n on 0 is definite, then f not equal to the primitive recursive set, this is the index phi m 0. So it is it's a little bit different, tricky diagonalization. And for this family, we can code this family into a structure as was described just above. And this gives a possibility to get this punctual degree spectrum. And relativizing this result, we can relativize this result to every function, to every computable functions with primitive recursive graph. So even such examples of the complements of lower cones are possible as a punctual degree spectrum. And so, returning to these questions, we get a positive answer to the first question. We get some set of oracles when the complement of the degree spectrum is exactly the degrees is a punctual degree spectrum, and it's unbounded functions because if G is not primitive recursive, then G cannot be bounded by primitive recursive function, because otherwise G must be primitive recursive itself. So here G is unbounded, and in fact, for some bounded G, primitive recursive bounded G, we have negative answer. And I must finish. I'm finishing just. It's the last slide, showing that in the complements of the degree spectrum, punctual and Turing degrees, we know that here it's possible that one degree spectrum is a union of two different degree spectra and comparable degree spectra. So it's so for example, we can take in Turing case, it's my result from 2007. If we take low sets C1, C2, then the complements of lower cones, the union of these complements is the degree spectrum of structure, and it is a join of two another structure. So computing one specific structure is equivalent to the computing another structure, one structure and another structure. So it is just if you compute a structure A, then it means that the A they compute some structure A1 or compute the structure A2. And we can get the same results for punctual degrees. So exactly, if the graphs of functions G1, G2 are primitive recursive, then the union again is degree. So again, we have this this effect. And so, thank you very much. Thank you for your attention.
So thank you very much. Is there any question? No question. And in the online audience? So I guess everything was clear. So thanks again for this very nice talk. So let's thank the speaker again.